presentation will be given by Jos van Westende, who's working for Deltares, and he's going to present some results about dynamic simulation of typical gas system using Wanda.
Yeah, thank you very much. First of all, let me tell you something about Deltares itself. Deltares is a knowledge institute that actually has a core business of defending the Netherlands against attacks from the sea. So then now you might think, okay, this is a little bit different from oil and gas. But within Deltares there's a small group which deals with industrial flows, about 15 people working there. And the industrial flow actually tackles flow problems related to transport of fluids and also gases. To do such flow problems, the way we solve that, we use a program for that, Wanda it's called. Wanda is, you could compare it a little bit with Bosch Fluids, the first presentation that we talked about. Wanda also has got a module which we call liquid, and with the liquid module you can compute pressure waves through complex pipe networks. But besides the liquid module, we also got a gas module in which we can compute compressible flows. We got slurry module and also a control module in there as well. But for today I want to talk about the gas module and how we use this module actually to tackle some flow problems in gas systems. Well, first of all, what's actually the gas system that I'm interested in? Well, examples are actually a gas production site, compressor blending station, or for example steam power cycles. Mainly we have done projects for gas production sites, and you see a schematic on this figure. So we've got a reservoir from which natural gas is coming via a well tube, and at the top of the Christmas tree you've got here a choke valve, and then you get via a transport line it's being transported towards a treatment plant. Well, typically for these gas systems is that you've got high pressure zones and low pressure zones. So typically the choke valve separates the high pressure from the low pressure zone. And because to get transport lines capable of that they can cope with high pressures, you need to have very thick-walled pipelines, and they are more expensive. So therefore, what people do during those, when you're in the engineering stage, is that you actually have the pressure rating of the equipment such that it matches the needs, because in that way it's economically the best way to do. However, during normal operation that's just a good way to go, but what happens if you've got an incident and a high pressure zone is connected to a low pressure zone? Well, in that case pressure waves will go through your transport system, and also the initially low pressure zone, which has got low pressure rating pipelines, may get damaged because the pressure gets above your maximum allowable incidental pressure, the MAIP, and therefore you get a risk of damage or rupture. So in order to actually understand whether you do have a risk of this damage or rupture, you need to know what are the excessive high pressures that can occur during such an incident. So we need to in order to say anything about it, we need to make an estimate of the maximum pressure that occur. And well, usually what actually was done in systems to protect the system from high pressures is to use pressure relief devices. Well, pressure relief devices, in order to reduce the gas pressure in large transport systems, you need to get rid of a lot of gas. So those pressure relief devices, if you use a PRV for example, they are very large then. And what's more important is that there's increasing criticism against venting or flaring of hydrocarbons into the atmosphere. Especially, I mean, Ruud Henkes mentioned also in his presentation this morning that you can have sour gas, but that's especially not done if that goes into the atmosphere. So what's then an alternative? And that is safety instrumented systems, also called SIS or HIPS And an example of such a HIP system is, for example, shown in here. So instead of just transporting the gas via your transport line, you have the gas transporting through a HIPS valve. And a HIPS valve is a valve that closes very fast, and it will close once the pressure downstream of this HIPS valve is above a certain critical level. So if you want to use such a solution, and actually the ESME in '96 they actually made some comments in their standards, and they said, okay, you can use such systems to protect your transport line, but then you actually need also to do an assessment of the maximum pressures. Okay, we need to do an assessment of this maximum pressures, and well, if you go a slide back, these systems, I mean, the reservoir usually is in the order of 3 kilometers depth, and your transport line, maybe you've got several production sites all connected to the same treatment plant, but they're located maybe in an area of several kilometers as well. So that means that the transport systems that we're looking at is in the order of 3 to 10 kilometers. So that's actually quite a large system. Actually, it's so large that in this case often you can get rid with just a 1D simulation, because what happens along the length of your pipeline is more critical than in the cross section. And the most important thing that we're interested in are the pressure waves that move through your pipeline systems. Another thing which is very important is the dynamic behavior of components, and also, for example, failing logic. So if you want to simulate an incident, then actually you need to know what actually triggers this incident. Is it a component that fails? For example, a choke valve that breaks open such that the CV of the choke valve increases to a large size instantaneously? Or is it maybe that logic fails, and well, how do you put that in your model? Well, further, you have that if you do have a dynamic behavior of your model, that may result in changes in the system, and those changes may lead to shock waves. Actually, they're quite comparable with water hammer shock waves, but if you go to gas systems, then you've got also that the density will change because you've got incompressible flows. So that's the fourth bullet. Expansion effects of gas must be taken into account. And that means that you need to have a good equation of state, but also heat transfer and elevation effects of your system play a role. Well, elevation effects actually only play a role in the well tubing, because you've got elevation of 3 kilometers difference, but if you just talk about 50 meters elevation difference for a gas system, that's not really important. And if you do dynamic simulations, actually that allows you to determine what are the maximum pressures that occur in your system, but you also got a better grasp of what the maximum pressures is. So you need to make less assumptions, and therefore better engineering is possible. So you can make, for example, if you can make these assumptions less, then, for example, you do not need to put in a vessel of 100 cubes to store some extra gas, but 20 cubes may be already sufficient. So there can be quite a large investment difference. I mentioned here shock waves, and that's actually typically what we see in the projects that we do. And typically problems what we have is that you've got a reservoir with connected to natural gas, and during the startup phase your choke valve breaks up. So actually all the gas is just standing still, and then you want to start your operation, but your choke valve does not open to the maximum controlled normal operating CV, but it just breaks open. Now, and to see what then a shockwave actually does, and I've got here a video. So this is a video of what happens when when a shock wave goes into your system. So this is a simulation in which on the left hand side initially you've got a very high pressure, and on the right side you've got a low pressure, and at T0 the two pipes, the low pressure and high pressure pipe, are connected and a shock wave goes through your system. Well, the difference with a compressible flow is that you've got the rarefaction wave going into your high pressure pipe like this, and you've got a compression wave going into your system on this side. But at the same time, that's not all what happens, because you also got your expansion effect of the gas, and that's typically what you see over here with the temperature. What I need to say is that the blue line is an adiabatic system, so no energy goes into your system, and the green line, I put the heat transfer coefficient so large that actually I want to try to make isothermal behavior, which is, except for this glimpse, almost the same. Also what happens. But you see that the pressure actually, or the temperature decreases if the high pressure and the low pressure pipe gets connected, and, well, we start again. And indeed you see the temperature goes down, and due to advection this low temperature is also advected in the low pressure pipe. And that results into also a discontinuity in your flow, which you see over here. So this is the density of the flow, and this is in the end the Mach number. So you see that if such a high pressure tube and a low pressure tube gets connected, then pretty quickly you end up with very high flow velocities. And this is a pressure difference of only a factor of 4, so from 100 bar to 25 bar, so that's actually quite small. In reality, the pressure differences may be much larger, and therefore also the Mach numbers are larger and the temperature decreases are smaller. Interesting to see here is that the isothermal behavior does not show here the discontinuity. So that means that if you want to do the simulations in an easy way and then leave out the temperature effect, that actually, well, actually you leave just out a little bit of physics. The good thing is that the maximum pressure still gives you a good example, a good measure of what happens in reality. So this is, well, with isothermal behavior, you still may get rid of it, or you still may get sufficient good answers with respect to maximum pressures, but still I think that if you can include adiabatic behavior, or if you can include the insulation of your pipes, that makes the results closer to reality. So that's about the shock wave. So this is what actually a typical example what I showed with that you can do with Wanda Gas. And Wanda Gas, actually the methodology of it is similar as Bosch fluids. We use the method of characteristic to compute pressure waves in the network. It's a 1D code for calculating fast transients, of course. And we take the full thermodynamics are taken into account. So that means conservation of mass, and energy. And besides that, until now we've used only ideal gas law and additional compressibility. We did make also comparison what happens, especially with the shock tube experiment. So that was this experiment. What happens with that problem if you use real gases and compared with ideal gases? And then we found that actually by tuning the parameters, the Z and also the gamma, so that's the ratio of specific heats, if you can choose them in a nice way, in a good way, then actually you're always on the conservative side. In future we want to also include the real gas, of course. Well, I want now to show you actually 2 examples. What happens and how you can actually use Wanda to compute the maximum pressures, and then also how you could design some additional core components such that you could meet all the criteria of the system. Well, the first example is, well, this is my base case without any safety. It's also from a production site, so I've got a reservoir over here. Reservoir is located with 3 kilometers depth. It has a bottom hole well pressure of 400 bara, and therefore the closed-in tubing head pressure is 315 bara, so that's a strong one. The gas is like this, so it has got 18 kilograms per kilomole, which is comparable to Groningen gas. Compressibility of 0.9 and a gamma of 1.6. These are a little bit values which I've seen during projects often. The plant operating pressure is 75 bara, and the maximum allowable pressure of my flow line is 85 bara. So these just numbers which I just figured out. The maximum production of my choke is when the choke is at a CV of 5 use gallon per minute per square psi, and it results in a mass flow of 5 kilogram per second. So that for the oil and gas, that's about half cube, normal cube per day. It should be million actually. So I forgot a small factor. And that results in a flow tubing head pressure of 309 bara. So actually that's quite close to the closed-in tubing head pressure. And now the scenario that I want to show you is what happens if this choke valve fails during the startup. So my CV goes from 0, in this case, to, let's say, 20, which is not what you can see here. Well, what you see is then actually that pressure wave goes through your system. So you've got here the choke valve. Because at T is 0, there's a big pressure difference between your upstream and your downstream side. And when the choke valve breaks, then you see nicely that expansion waves go into the upstream side, and a compression wave goes in this side. What you also see is that the downstream of the choke, the pressure goes up a little bit. So you especially see it on this one. At 5 seconds, the pressure is a little bit higher. And upstream of the choke, the pressure goes down. So you see it over here. What has been done in modeling previously is that actually the pressure waves through such a system have not been computed. So what do you do then? Well, the best way is then to keep the pressure upstream of your choke constant to be the closed-in tubing head pressure. But if you see that the pressure already decreases quite strongly, and that depends of course on the CV of your choke valve after breakout, but if this pressure goes down, then that means that the pressure wave that goes into your low pressure system is also smaller. So that means in order to do, when you do these dynamic simulations, you can also avoid that you are too conservative as well. And these are done the pressure in the flow line, the maximum pressure, and the maximum pressure occurs upstream. So this pressure is doing this in time. So at T is 0.1 actually. I started the production, but the CV breaks out, and then pretty soon you got the shock wave. So immediately increase to about 82 bara, and then you've got a gradual increase of your pressure. Now, it's very obvious that after about 1.2 seconds, approx, the pressure at the flow line exceeds the maximum allowable pressure, so this is not good. In the end, the maximum pressure downstream production side is about 110 bara, and the average flow through the choke is in the order of 19 kilogram per second. So that's 4 times more than the maximum flow during normal operation. What can you do? Well, you can install a HIPS. And a HIPS can be designed in such a way that you've got a pressure sensor downstream that measures the pressure, and when it exceeds a certain level, then this valve closes as fast as possible. Now, what is fast? Well, a valve of this size, which you normally see, can close in, well, if you can make it close in 1 second, that's extremely fast. But then you also need time, because this sensor needs to to measure the pressure correctly, and you've got some the measurement signals that go through your system, logics, and also the actuator, for example, needs to be pressurized. So there's also some time involved with that, and we take a response time for 1 second. So a total closing time of 2 seconds for a HIPS valve is generally accepted in these valves, for these valves. And then what happens? Well, if we take a set pressure of 90 bara, which is of course too large, but then you see that when the 90 bara is met, then 2 seconds later the HIPS valve closes and your pressure does not increase. So that looks good. Of course the set pressure is way too large, so let's decrease the set pressure, and then the HIPS valve should close more quickly. Now, with the set pressure of 80 bara, then you see, well, that the maximum pressure is only 87 bara, so it's still above MAIP, but we're getting close. So still, we would say, okay, set pressure is too high. The problem is that this pressure increase goes from 75 to 82 bara immediately. So that means that if I'm going to make a set pressure of 75 bara, this will not change. So that means that in this case, if you would take a HIP system to protect your flow line, actually your HIP system is just not good enough, because you cannot make your valve close faster than the 2 seconds. So it's just the response time of that system. So you need to do something else, and there are actually two solutions that we've encountered in projects, mainly actually that also our customer, our clients, they proposed what is a certain solution doing. And one is that you include an extra orifice, so you put an extra restriction upstream of your HIPS. And the second one is, well, still to use a PRV, which is actually not nice, because then you're venting or flaring again in the atmosphere. But then let's see what is doing this. I did some fine-tuning already, and I found that for the additional RO you need a CV of 20, which is good, because for normal operation we have a maximum CV of 5, so this is larger, and that means that during normal operation this restricting orifice probably will not have a significant effect. And for the PRV we take a CV of 75, which just makes sure that enough that the pressure does not increase. And then the results with the additional provisions are like this. So the bottom one, dark green, is when you include the HIPS with a set pressure of 80 bara and an additional restricting orifice, and then you see nicely that the first increase of your flow or of your pressure does not increase so fast, because you've got extra resistance, so that's logical. And also the maximum pressure reaches only 85 bara before the HIPS valve closes. So you can make tuning with the restricting orifice such that you are just on the safe side. On the same time, you can also say, okay, let's see if PRV is helping out. And if you take a PRV with a set pressure of 83 bara, which is just a little bit above the HIP set pressure, which is very common, because you want, in essence, you want the HIPS pressure to start closing before the PRV. We put in a 95% blowdown and 0.1 second response time. That's also typical results that we got from the industry. And then you see that 0.1 seconds after the pressure has exceeded the 83 bara, the PRV opens, and you see here a small dip in your pressure. And that makes it just that the pressure remains under your under the maximum allowable pressure of your flow line. So this actually would help to protect your system. So for a PRV we would have a release of 5 kg in 1.5 seconds, and for a choke the average flow goes down from 90 kg per second to 16. But that's not all, because for example, if I'm going to change my model slightly, let's say this flow line is it's about 2 kilometers long and it goes through a hilly terrain, then there are locations at which you may encounter slugs. For example, if your reservoir is also producing some liquids, then slugs may arise. So let's assume we've got a slug in this flow line which is located 200 meters from the production site and has a length of 50 meters, and let's say it's water. Water is just conservative because high density, so large inertia makes it move less fast. So the slug in the flow line is modeled by its inertia and friction, and the rest we take the same gas production site and also the same scenario of the fill. But now what happens is totally different. So we see here the dashed line, the black dashed line, that happens without the slug. But if you include the slug, is that actually the gas, the shock wave impacts on the slug, but the slug is still not moving, so actually it is acting as just a fixed boundary, a closed valve, you could say. So the gas, the shock wave reflects and goes back, and in that way the pressure goes up very quickly. Only after a while the slug gets accelerated, and then you also see that extra volume is created, but that's already far too late. So what can we do? Well, let's install the HIPS again to see what happens. But what we already mentioned, to put the HIPS valve with the set pressure below 80 bara, now it has got no point because you've got an increase of 75 to 82 bara instantly. So set pressure below 80 bara, it does not make sense. And then you see that your maximum pressure still is 95 bara. So that's much larger than without the slug. Of course, we can also make designs for alternatives, and in order to keep it without the maximum pressure that are allowed, we have to use an orifice, an additional orifice with the CV of 9, which is still larger than 5. So for normal operation, it would be okay. But I try to use also PRV and get the pressure below the maximum allowable pressure, and that was not sufficient. So actually, if slugs may occur in your system, then in this case, PRV is actually not an option anymore. So conclusions that we can draw on this on these two examples is that if you do a dynamic simulation of your system, then you can actually give detailed information on your unexpected incidents. I only showed here the pressure, but also you can get results of the temperature of your gas and therefore the effects on the pipe materials. So other physical quantities are also available, and that gives us the choice that we can do better engineering possibilities, and therefore we can get fit for purpose design. So it's not only safe but also economical. The second point is that a relatively small change, well, you can argue if it's small or not, but a change in your system, in this case a slug, can have a very large effect. So you really have to make sure that the system, the worst case scenario that can occur, that's also a scenario that is realistic. And the last thing is you need to check whether your HIPS system is actually fast enough. And if that's not the case, you have to take additional measures, such as a restricting orifice, PRV, or maybe go for another HIPS. And finally is that if you do have done this check, then you also need to check, of course, if the normal operation is still not affected too much. So this is about my presentation. Thank you for your attention.